Let's see. Okay, first, I would like to thank all the organizers for their invitation, and it's a great pleasure to participate in this workshop. Okay, voila. So today I will talk something about ISS analysis, and this is a joint work with Junzhen from Southwest Georgetown University, and he is now in Montreal. Okay, and the topic of ISS, actually it has been taught several times, okay, in this workshop, either for panel talks or in the interactive sessions. So you must familiar already with all this his history and all these notions. Okay, so you know that they start from the work of Sundak for finite dimensional systems, and the early work for extending the notion of ISS to the PDE systems start around 10 years ago. So I mentioned some people who made some important and original contributions. So there are many results. Okay, it has been published recently. Okay, you can see the comprehensive series in the paper of Jinko and Perth, and also in the monograph of Karafalis and Kostic. So for PDE systems, the disturbances compare mostly in two places. Okay, can be distributed over the domain. For this kind of problem, actually, there's no fundamental difficulties to extend the notion of ISS. However, for the disturbances located on the boundary, it is a more challenging problem. But this actually motivates many people to work on that, and they have obtained many interesting results. I think that including someone in audience. I just mentioned some of them. It's not a complete list. For example, we can use spectral decomposition, finite difference scheme, etc. Actually, just try to estimate, to establish the ISS image directly based on the solution. Okay, there are another method that's based on monocity method. Actually, it's try to transform the binary disturbance into domain without invoking the time derivatives of disturbance. We can use other method, for example, the Georgi iteration to directly construct estimates, or in a more generic setup. Okay, we can use semi-group and use concept of admissibility that has also been mentioned several times in the previous talk. And also other method can use. Okay, there are many. So the results I will present today is based on the Lyapunov method. Obviously, Lyapunov method is one of the main tools for stability analysis. And in particular, if we want to establish the ISS estimates, so the Lyapunov function appears to be a very convenient way. So in order to apply the Lyapunov method, we have to start by constructing the Lyapunov functions, or start by a convenient candidate. Okay, it's not okay for linear systems. Okay, finite dimensional or non-finite, infinite dimensional systems. Okay, we have a relatively good idea about the form of the function or its candidate, but it's not the case for nonlinear systems. Okay, we do not yet know, or do not have, do not we have constructing a function in a systematic manner. But for some class of systems, for example, for parabolic systems, parabolic PDEs with Newman or Robin binary conditions. Okay, if we are looking for establishing the ISS at P norm with P bigger or equal to 2, actually we can choose a functional of this type. Actually, this is the P norm of the solution. Okay, so to illustrate the application, we just consider, you see here, a simple parabolic equation with F as the endowment disturbance and D0, D1 are the dependence located on the left and the right band. Okay, so we suppose that we just consider in this example Robin binary conditions. So through this example, I will show that okay, actually an application of Lyapunov method is quite straightforward. Okay, so we are looking for the ISS in the Euro sense. Okay, here suppose that means we try to find the function beta, which is a KR function, gamma 0, gamma 1, gamma are functions of class K, and we try to establish this these ISS estimates. Actually, okay, we can also show that beta decays exponentially, so it is actually exponentially ISS. Okay, so to prove these results, we'll consider these Lyapunov functionals and we'll compute its time derivatives. So what we need actually is the Young equality. This is a standard tool we use in Lyapunov analysis, and we also use a version of Mettinger's inequality given below. So this is actually two inequalities we are going to use. So now we compute the time derivatives of L2 norm, and we get this equation. Okay, now we do some execution by part and apply the initial binary conditions. We can get this one. So now we apply Young's inequality to the term in blue color, and we apply the Mettinger's inequality to a term in red color. So we can write, we can obtain this term, and then easily find the estimates of the time derivatives. Okay, you know that because K0, K1 actually are the gain of the physical control on the boundary. So we can choose the value of K1 and K0 so that these two inequality holds. So we can now get immediately these estimates, and by using the Gurwell inequality, we can get the estimates of a solution, which shows that the system is exponentially stable, exponentially ISS in L2 norm. So it's quite easy and quite straightforward if we're looking for L2 norm or LP norm with P bigger than 2. So the question is that, if we want to establish the ISS in LP norm with P between 1 and 2, can we still use the same form of Lyapunov candidate? Okay, so to answer this question, we just verify two cases. First case is for case where P equals 1. But you know that the function of absolute value is not differentiable at the origin. So we already have the trouble, and in addition, in general, these two functions are not equivalent. Actually, depend on a solution which is unknown a priori. Okay, so actually we cannot compute the derivatives of L1 now, or in general for a system defined on high-dimensional spaces. Okay, the same. In the case for P between 1 and 2, I will compute again the derivatives of the LP norm of the solution for system 1. So by direct computation, we can get expression, but we see clearly this term is singular at the point where P equals 0 if P, W equals 0 if P is smaller than 2. Okay, and actually P between 1 and 2. So still we have problem with the computation of the time derivatives of LP norm of the function. Okay, so in order to overcome this problem, so what we have tried out is to use the approach of approximation of Lyapunov functional in order to establish the ISS in AP norm for P equals 0, for P between 1 and 0. Actually, we are wanted to fill the gap, for fill the gap for the in existing literature. Okay, now, so the approximation of left functional we are looking for should be first second order continuous functions. So it has to have the following properties. First, it should be a function positive. It takes minimum at 0, and it should be a convex function. Okay, this is a natural requirement. Okay, for this function. In addition, we also add some conditions here. I will show later on. Okay, how to use the condition in the ISS analysis. Okay, here C1, C2, C4, C3, etc. are all the positive constant. Okay, so a simple function can take is of this form. Actually, this function of absolute value is just replaced by a polynomial for the point around the origin of this function. So in order that this function to be C2 continuous, so we have to impose this condition, which actually will simplify this function. All these parameters can be expressed in terms of A0. So we have this function. Actually, the choice of A0 can be arbitrary. For example, if you choose value of 8/3, we get a function of this form. You can choose other values, you get another form of the system. But either way, okay, this condition can always be verified, and also this is a convex function. Okay, for example, okay, for the first one, if we take A0 equals 8/3, we get this function. So this is the form this function. For this point, we take, for example, tau equals 0.3, or take tau equals 0.1. So we see that this is the function. Okay, we are going to use, and when we take tau goes to 0, so we can push the curve towards the origin. This function we're going to use. Okay, so this function satisfies all these properties. Actually, it takes 0 as 0. It is a convex function, and also it's a first derivatives. The absolute value of first derivatives is always smaller than 1, and this convex function with these properties. Okay, we're going to use in our analysis. Okay. So, now, we can compute the integral of this function rho tau, and the integral is lower bounded and upper bounded by these two functions. So now, if we take tau tends to 0. Actually, this function, actually the integral of tau rho, will turn to the A1 norm of the solution. So, okay, we can see that the integral itself is not a valid Lyapunov function, or it's not a valid candidate for a Lyapunov function because it does not take equals 0, okay, at 0. But when we take tau tends to 0, so it can be used as an approximation of a coercive Lyapunov function. It's the same for case, okay, if P is between 1, is bigger than 1. It's the same case. So for AP now with P bigger than 1, we can take an approximation of this form. So I will illustrate how to use this one to establish the ISS for our parabolic equations. Okay, this equation this is a parabolic equation we consider, and this is a quite unique setting with conversion varying in the domain with some nonlinearity, and we consider first the problem with the Robin and the Newman boundary conditions. We impose some regularity conditions, okay, which are necessary for well-positiveness. Okay, this problem we are looking at, and so we are going first to establish the ISS in A1 norm. Once again, this is a standard definition, a standard property we are looking for. Okay, so now we are going to impose two sets of assumptions. The first set of assumption is to guarantee well-positiveness of the considered problem. So the function A is lower bounded. Okay, it's positive it's a positive and the lower upper bounded. This is an assumption about the nonlinearity, and this is the boundary, this is the initial value of the disturbance. So by using all this, these assumptions, we can prove that the considered problem is well-positive in the sense that it makes a unique classical solution. Okay, this is the first set of properties. The second set of assumptions is about the ISS. Okay, actually, this is about the stability of the system. Okay, So based on these assumptions, okay, we can claim that this system is exponentially stable in A1 now, and we can also give the ISS estimate, okay, which takes the following form. Okay, so I will show some details actually to illustrate how to use the properties of this function or tau. Okay, so we take this integral of rho tau as a candidate, and we compute its time derivatives. Okay, the computation is quite straightforward because we know that the function rho tau is derivable, so we can directly compute this one, and then we can get all this term. Already you can see that this term in blue color, okay, it involves the tau prime, which is always positive. Okay, depend on our it's because the function is convex, so we can skip this time in analysis, and then we can estimate every term, every integral in this expression. Actually, for example, here we see that okay, the amplitude of our rho prime is less than 1. Okay, this first one, and also we see that okay, these two rho prime multiplied by W is positive. So we can get this estimate. Okay, similar, we can estimate other term. For this term, actually, we can use a property of the tau, and also use the upper or lower band to give a term which depends on the tau. Okay, and we can also estimate term related to the nonlinearity. We get this form. Okay, actually, it's also a term. Okay, with tau as coefficient. So we can compute the other term, so we'll get a quite similar form. That means a term depend on tau, and another term will depend on tau. So now, if we put everything together, all them together, we get the estimates of the time derivatives of this function. So actually, okay, we can rewrite them in two terms. The first actually is used to guarantee stability. A actually captures the norm of disturbance F and D, and the B of T is term with tau as a coefficient. Okay, we know that actually tau B of T is bounded function, bounded time function. So now again, apply the Borel inequality, and we can get estimates of this function in this form. So actually, now if we let tau tends to 0, so the last term will disappear. So we get this form. Actually, the right-hand side of the function turns to the L1 now, and the left hand of this function, this equality becomes this form. Actually, this is what we're looking for. It is ISS estimates in L1 now. So we can prove the results. Okay, so now, how about the case where P is bigger than 1? So we can also prove that the system, 3 with Robin and the Neumann boundary condition is exponentially ISS in LP norm with any P between 1 bigger than 1, and the estimates is given specifically in by this form. Okay, well, we can see that by this form. So the proof actually is the same. Okay, the procedure is the same. Okay, we start by taking the integral of rho p power p as an approximation of the LP norm of the solution, and then we'll compute its time derivatives and use a procedure to establish the ISS argument, ISS. So during the computation, actually we'll use another one, that means based on lemma 2, actually about all the properties of this function rho tau. And also it is easy to verify that this function is non-zero. So based on all this, we can compute directly the time derivatives and to get these estimates. Okay, so this actually we have proved the exponential stability of the problem of this parabolic equation with Neumann and the Robin boundary conditions. So we can actually extend the same, technique to establish other types of ISS. Okay, the first one is we can also establish the ISS in weighted L1 norm for the semi-PDEs with Dirichlet boundary disturbances. Okay, so specifically we will consider the same parabolic equations with Dirichlet boundary condition given here. Okay, so we can prove actually that the system is exponentially ISS with a weighted A1 norm. Actually take this form. So we're going to compute the weighted norm. So phi is a function, okay, given here, actually phi is a solution of this differential equation. With initial value equals 1, boundary value equals 1, and the initial value bigger than 1. Okay, we can get this one. So to prove this, we'll use this form of candidate, and then compute its time derivatives. Actually, this integral is in general an approximation of the non-coercive functionals here, because actually phi can take value can be 0, okay, at different point, not only at the equivalent point. So actually, it is an approximation of no coercive Lyapunov function. Okay, actually, we can also obtain other extensions. Okay, for example, if we consider a system in a more generic setting, for example, in all this space, we use a functional of this type where G is a unit function, so we can establish the ISS in IG norm for Robin and Newman boundary conditions. If we use the weighted function of this form, we can also establish the IG norm can establish the ISS in weighted IG norm for systems with Dirichlet boundary conditions. Okay, this is the results reported in the preprint we put on arXiv. Okay, also recently in a paper that were published in next CDC. So we can also establish ISS in Sobolev space. Okay, actually we start by consider problem with the in-domain disturbance, and we can also extend the results to problems with boundary disturbances. So okay, this is a very fresh idea. So we hope that we can get some new results, or maybe it can get nothing. Okay, everything possible. At least, for example, we can try to see how, if it is possible to establish the LP norm, but not the weighted LP norm for the parabolic equations with Dirichlet boundary conditions. Okay, this is one thing we can try to do. It may work or it may not work. We do not do it yet. Okay, so I go very fast. So actually, it covers what I plan to present today. So thank you very much for your attention.